Page 589, lesson 9.7 is on linear, quadratic, and exponential models. So if you look at this concept summary box, just a reminder of these different types of functions. Linear is going to look like a straight line, and it's in this form y equals mx plus b. Quadratic is either a U-shape or an upside down U-shape, and it's in this form. It's got an x squared term. It might also have an x term and a constant, but it doesn't have to. And exponential has the variable x as an exponent, and these are graphs where they can either go like this one where they increase and go up, or you could have exponential decrease where it's going down as well. So in problem 1, they're asking us to graph the set of points and tell which model is most appropriate for the set. So if you look at part A, if you graph those points, this is kind of making a U shape here, so that would be a quadratic. Part B, it's not a straight line, it's not a U shape either, and we're going to assume they've given us enough points. I mean, technically you could say, well, what if there were more points over here and it made a U shape? Well, we don't know that. We're going to just have to say they gave us enough information to determine that this would be exponential. And C, these do line up with each other. This makes a straight line, so that would be linear. So if you look at the got it one, they're wanting us to graph these points, kind of the same idea here. So if we graph these points, we've got 0, 0, 1, 1, negative 1, negative 5/10, and 2, 3. So at first it kind of looks like they almost line up with each other, but with that last point, for sure they don't. And so this is going to be exponential for part A. Part B, same idea. We'll graph these points. Negative 2, 11 is going to be off the charts up here somewhere. And regardless, though, we can see that the graph went down and then it starts to go back up again. So this would be quadratic. This is going to be a parabola here. Besides graphing the points, another thing we can do is look for differences between our x values and y values. So if you look at this first table here, every time the y values are increasing by 3 and the x values are increasing by 1, and that might ring a bell with something we've done before. Change in y, change in x is always the same. The slope is always the same, and so this would be linear. Okay, so anytime if it's linear, we're going to have a common difference, which means we have a constant slope. In the second example, x is increased by 1 each time. The y values are doubling each time. So since they're doubling each time, this is going to be exponential. So exponential, what happens is we are either multiplying or dividing by the same number each time. And that's with the y values. So the y values we're multiplying or dividing. The x values we're just adding the same number each time. And then it's kind of interesting here with this last one. The x is increased by 1 each time. If you look at the y values, they were subtracting 2, and then they added 2, and then they added 6, and then they added 10. And it might look like there's just no pattern going on there at all, but those are called the first differences. Now if you look at the difference between those numbers, so from -2 to 2, that's adding 4. From 2 to 6 is adding 4. From 6 to 10, that's adding 4. Those are called the second differences. And when the second differences are all the same, then it's quadratic. Second differences of the y values. Okay, so it's constant or they're the same as each other. So two other comments about this. One is that it's possible that when you're doing these problems, they could skip over something. So like, let's say on this first graph, let's say they didn't put the 0.05. So you might say, oh, well, this went up by 2, and then this went up by 6. But if you divide that out, you still get that constant slope of 3. Okay, same thing with these other ones. I mean, they could technically switch and actually skip over a point. And that brings me to the second point here, is that your other option you have besides doing all this stuff they're talking about, the other option is you could just graph the points and then see what it looks like, just like we did at the beginning on example 1 or problem 1. Just graph the points and see, does it make a straight line, or is it a U shape, or is it looking like an exponential increase? So if you look at problem 2, you can see part A, x's go up by 1 each time, y's keep subtracting 4, and so that would be linear. Its slope is -4 over 1, or -4, constant slope there. For part B, the change in the y values was kind of all over the place, but then when they found the difference of those numbers, it came out all the same. So second differences were the same, means it's quadratic. And then if you look at the got it, I'm going to rewrite this using a table. So x's are going up by 1 each time. And kind of if you look at this, especially with these last numbers, you might notice these are doubling each time, and it actually goes back all the way. So y values are being multiplied by 2 each time, so that would be exponential. And again, if you graphed the points, otherwise you'd be able to see that exponential curve there as well. In the real world, data very rarely is exactly going to be linear, exponential, or quadratic, but we can look at it and see what it would be the closest to. So if you look at problem 3, they have data for values of a used car over time, and they're asking which function best models the data. And so what they did here is they divided out y value and the next y value, and they're getting about the same answer. What that means is we're multiplying, let's say this 12,575, we're multiplying that by about 88 hundredths. We're taking about 88% of that value to get to the value for the next year. Then we're taking about 88% of that value. Okay, next one, notice it's 87%, but it's almost the same. And then again, 88%. So those are all really close to each other. That means we're multiplying the y value by the same number each time. And so that means it is going to be exponential. So if you look at the got it, they've got annual incomes for a small theater company. Which type of function best models the data? So rather than graphing these, I'm just going to look at these numbers and say that they're not really changing a whole lot from year to year. And if you go through this is plus 476, this is plus 485, plus 480, plus 480. Okay, so those are all really close to each other. And so linear would be the best type of function for this one. And then it says write an equation to model the data. So a linear equation, y equals mx plus b. Probably what I would do is just say this first point at year 0, that's going to be your y-intercept. So 18,254 goes in place of b. And then the slope, if you look at these numbers, they were off a little bit. I'm going to say they were all pretty close to 480 though. So I'm just going to say my slope is about 480. And then that would be the equation for that. And then going back to, I didn't mention this over here, but on the previous problem, it did talk about writing an equation for that. So we did this back in lesson 7.7. Lesson 7.7, we talked about, this was our formula for exponential. A was the initial amount, and then B was the growth or decay factor. It was 1 plus the percent rate of change as a decimal. And so on this one, that's how they came up with this. The initial amount was 12,575. So that's what they put in place of the A. And then we're multiplying it by 88% about, so it's about 88%. You could say then it's a 12% decay, we could call it 12% decay. So if you did 1 minus 12 hundredths, that's how we would get the 88 hundredths, which I know we already had that. So that's how they got that number. And then just the exponent is always x with that equation. So if you look at the lesson check, I'm not going to go through and graph all these. I think you guys can handle that, but either graphing or looking at the differences in the tables. So I'm going to tell the answers here in just a second. So if you want to try and work these out before I give the answers, would probably be a good idea. Probably be generally a good idea to do that as we do problems like this. So number one, that ends up being quadratic. Looks kind of a quadratic shape on that graph. Number two is linear. Each time what's happening is they're adding 3 to the y values. So change in y over change in x's. They're actually changing x's by 2, so it's actually 3/2 or 1.5 would be our slope there, but that is linear. On number 3, the x's, they went from -1 to 0 and then 2 and 3, so they skipped over 1 something, which if you graph this out or if you work it out, it's going to be 1, 2 would be the number that should have been there, but they can skip numbers if they want. Anyway, if you graph it, that would be another way to figure this out, that it's exponential, and what's happening is they're dividing by 2 for the y values, or you could say multiplying by 1/2 to get their next y value each time. So this gives you an idea of how to determine if something would have a linear, quadratic, or exponential model.